All right, so let's start the second session. Okay, so the second session, we will hopefully can get into the point of predictive distributions. We want to get the point into predictive distribution. As I mentioned earlier, the problem that we want to have is that we want to know the new given the bar. So again, the bar, we know that T bar is a training data, right? So the T bar is T0, T1 until Tn. So this is, in other words, this one is your training data, the label of your training data. Yeah. Oh. Okay. Thanks. Yeah. All right. So it's coming up, I think, right? Okay, good. Okay, so this is again the one that we want to know. What will be the probability of the new price, the future price, given the prices that you learned in the past? And this one is very different from P W bar T bar. It's very different because the second one, number 2 here, is talking about your confidence level, your probability of your W. You are given the W and you know how bad or how good is your W. But it doesn't tell you what will be the probability of your health in the future. Of course, if your W is good, your predictive is good, you know that your predictive is good, but you do not know exactly how much is your uncertainty, how much is your probability. Does it make sense? You only know the probability of your W, your term. You know how good they are, how good the country is. But you do not know exactly the probability of your future price of your price. And that's something that we want to know in the predictive distribution. That we want to know not only the probability of PW, but the probability of this number one equation here, the probability of your future price. And that's more important for you. Because that really matters, right? The price of your car. Any questions here? Yeah. Exactly. Yeah. So if I say that in the past, my price of the car is 500K, 600K, sometimes 400K. There's a fluctuation of the price in the past. And you want to learn about the fluctuation, maybe some trend, and assume that the trend is linear, and you're pretty sure that this linear price in the past is very consistent. So assume that it's a linear line. Of course, in the future, you can predict this based on your curve, right? And you know that it's going to be a good curve. But you only know about the probability of this curve. You do not know the probability of the price in the time. You know perhaps the price, the predicted price. You know the predicted price of the curve, but you do not know the probability of this price. And that's something that we want to know. The probability of the price in the future. And that's the expression here that we have. The probability of T new given T bar, and T bar is the past prices. It is more important than number 2. Any questions here? Okay, so Now, let me see if I can jump into this. Okay, so anyway, so there are some fundamental concepts that I need to teach you first, actually, before getting into distributions. But let's skip that one and let's learn that one when we are facing the problem. Okay, so anyway, so now number one here in the longer expression, it is actually the more complete kind of expression should be P of T star, or maybe, you know, P nu is fine. Do not make you confused. P nu given X nu is the, you know, the here that you want to predict. The here that you want to predict is X nu. And you have P bar, the past data, the past prices. And then you have X bar, the here in the past. And then you have alpha and beta, of course, because the alpha, you know, the hyperparameters of your prior, and beta is hyperparameter of your likelihood. And this is something that we want to know. And we can again reduce this one. I mentioned again equation number one then, that this is P nu given P bar. Okay, but actually in the given expression, there's a lot of things that we actually know, or assume to know. Okay, so in this case, the solution, there are two possible solutions. One is using Bayes theorem. You can express this in Bayes theorem. But in this case, we don't, in physical distribution, we don't use the Bayes theorem. But instead of Bayes theorem, we use marginalization. So we use marginalization or some rule to solve the problem. So how we can, if we have to express this in terms of some rule or marginalization, what equation it will be? What equation that we have to write here? Marginalization. Marginalization is always using integral, right? Using integral. So marginalization, as I want to remind you again. So if you want to marginalize B, so we have A and B, and if you want to know the PA, means that we have to marginalize B. And if you marginalize B, means that P, A combined with B, together with B, C, B. So this is all marginalization. Okay, so the same thing here. What would be P in this case? What will be the things that can give you advantage in terms of the information, but actually you don't have? You just use it for your purpose. Not P bar, unfortunately, it will be equation number 2 there. W is very important for you. It can predict your future, but actually you don't care about W. Right? To know number one, actually you don't care about W. W is only used in the training, but it's not useful in the testing. Of course, it's useful, but it's behind the table, behind the thing, it's useful. But not in the testing period of time. So that's something that we want to use, but we don't care. We don't care W, but we want to use it. Right? So in that case, we do integration of P nu combined with W bar given P bar. P of P W bar. Okay, so this is for marginalization. It's very useful for you because this is the first step in expanding your analysis. As a data scientist, if you want to go data scientist, you have to have this step before you are entering into further and further mathematical expression. If you do not know the first step, it's impossible for you to do the analysis. So this is the first step that's very important for data scientists to know what you have to do. Of course, as I mentioned, there is a Bayes theorem that you can expand with based on the Bayes theorem. But this is another possibility of expansion, which is called marginalization. If you know something that is not useful in the end, I mean, it's not really needed in the end, but it can be useful for your computation, then your way of thinking is that I want to marginalize based on that variable. Okay, so this is important, again, in practice, if you want to become a data scientist. All right, so anyway, so after we get this one, based on product rule, then you can expand this further. In product rule, you will have P, the new, let's see, given. So in this case, remember that if you want to expand this, P A given B, P B, P B, right? That's a product rule. The same here, B is W, A is a P new. So in this case, it will be given P is W, and P, if you want, you can put P of W given P bar, P W bar. Okay. So if you look at this one, what is this? What is the term? Yeah, so this one is actually number 2. This is exactly number 2. And how can we get number 2? From the previous step, full division, you can get number 2. All right, so that is useful. We can get the term from this equation here. Right, so that's the term, the second term. So let's look at the first term here. The first term here. So there are 2 terms. The first term and the second term. The second term again is a full Bayesian. And number 1, if you look at this, if you know W, do you need P bar anymore? Do you still need P bar if you know W? No, because P bar is already processed in such a way to give you W. Right? If you know W, you can predict the future already. You don't need to have P bar anymore. So in that case, because now by knowing W from the full Bayesian from number 2, then we can actually already predict the future. So that's why we don't need P bar anymore in the first equation. Become independent. Given or not given, it doesn't really matter. Because number 1 there is really to decide P new, to decide the price in the future, is enough for you to get it from W, from the curve. Is it understandable? Okay, I can give you the illustration. So basically, the curve here is W, which is Y, basically, Y bar of W. And the prediction of the future is P new here. This is X new. Right? To get P new, as long as you can have W, you can actually know P new, even without P1, P2 until Pn. Even though you do not know P1 until Pn, which is the dot distribution of data, you can still predict P new from W. So that's why you can remove P bar. Any questions here? Okay, so now we have 2 terms. So let's look at these 2 terms. So the second one is easy. So start with number 2. P of W given P bar equals to what? Gaussian, yes, Gaussian of what? Of always input W with mean of N with standardization of and Sn is defined in the previous page. Okay, so that is for number 2. So for number 1, we have P nu given W bar. So what is the correlation of, let me think. Yeah, so what is the correlation between T nu and W bar? So T nu have to be as close as possible with what? Have to be as close as possible with W bar, but in this case it will be represented by Y nu. Right? Remember, Y nu is the curve, right? And the curve has to be as close as possible to Tu. And Y nu equals to what? W transpose multiplied by nu, H nu bar, right? But we don't like H nu. Remember, it's polynomial function. We don't like polynomial function. We have to change that into phi nu. But because of the error, there is an error between the distance between P nu and Y nu, right? This one is plus, yeah, epsilon, right? And epsilon here is following what distribution? Gaussian distribution. So this one, the correlation here is Gaussian function of the input P nu with the mean of Y nu, and Y nu is W transpose phi nu. And the standard deviation of, yeah, and the previous computation is beta inverse phi. Correct? Any question, anyone here for this modeling? Again, the modeling is everything in data science. So you cannot, yeah. Remember that in the very beginning, that we have the data here, and then we have a line, and then we have a Gaussian function here, right? And what is the standard deviation of that? It's sigma square, right? Sigma square equals to beta inverse. Yeah, good question. So beta inverse is actually sigma square. It's a precision. Okay, any other questions? Okay, now, if you look at this equation, we have to do the integration. So the integration, you can consider these two functions, both of them are Gaussian. This one is a Gaussian function, obviously, because it is Gaussian. And number one is also Gaussian. If you want, with respect to W, if you want to consider W as the unknown, the W is unknown, right? W here is unknown. If W is unknown, what do you call the second term? What do you call the second term if W is unknown? It's not posterior anymore. Yeah, it's posterior basically, but it's good it's posterior actually, that's true. But now, yeah, it's a bit difficult to explain, but now you can think that this one, the first term here, the second term here, is actually the prior of the first term. And the first term is pretty likelihood. You can consider it that way, right? That W is unknown, the likelihood become likelihood in the first term and become prior in the second term. In other words, the prior plus prior and likelihood are Gaussian. Now, why is this important? Remember that case two consists of two things, right? This is case two. Case two has two things here. Case two has two things. The first one is called posterior or conditional distribution. The second one is what? Evidence. This is evidence of actually marginalization. And this marginalization assumes that both the prior and the likelihood to be Gaussian. And this is marginalization here that can give us the solution. Because if you look again, what we're doing here in this specific distribution, this one, the whole equation here is actually marginalization. Exactly the same as case two number one. So again, because it's exactly the same format as case two number one, then we can just use case two number one to solve this integration problem. This is difficult because of integration, right? But case two already solved it for us. Yeah, W bar is unknown. That we do not know. How can we know the W bar? Of course, you can predict with the second term. With the second term, you know W bar, but that is a prediction. Yeah, W bar is training, but actually you do not know that it's prediction. After you get the training process done, W bar is a prediction. It's not true in terms of trueness, but it's still a prediction, still a variable, still a random variable. And actually, we use that here, but what I want to say is that even if you know the second term and the first term, the integration is a big problem because the integration is difficult to do. But if you have the problem, the likelihood and the prior of both Gaussian, you can solve this integration problem using case two. Using case two here. Because case two already gives you the solution. This is the solution of marginalization. This one already gives you the answer. Okay. So now to solve that problem, we will use case two. Okay. So let's where is it? Case two. Yeah. Case two. So let's copy and paste this one. Oh, I actually already done that. So let's. Okay, so let's use. Okay, so let's do the matching. Okay, so this is case two. Now let's do the matching here.
So basically, we want to use this one, marginalization. That one is something that we want, given the likelihood and the trial. Okay, so in that case, we start with equation number one. Equation number one. For equation number one, y bar equals to what? Y bar equals to, let me think. Yeah, P nu. And A equals to, anyone? A equals to 5. And mu bar, mu bar equals to H mu. And B equals to 0. And L is what? L is here, right? It's like equal, and that's the same as that, which is theta inverse, which is theta inverse. Okay, that's L. How about A? A already defined. How about lambda? Lambda is the same as lambda is here, and that would be the same as that one, right? Is out of the sense. Fn. Okay, so everything is complete then. So now what we want is P of T star given X T star mu. Yeah.
Mu bar is mu.
Oh, good question. Yeah. And then yeah. Mu bar. So let me think. Mu bar is mean. That's what. Yeah. This one to be and okay, so P nu given H nu P bar of beta equals to, this must be Gaussian according to the equation here. According to this equation, it will be Gaussian. Gaussian of P nu with mean of let's say M nu and H nu. Okay, so that's something, and nu is something that we want to know, and nu equals to, and nu is equal to this one. A is 5. A is 5 multiplied by n. Okay, and then H nu equals to what? H nu is this one then. L inverse means beta inverse I plus A is 5 transpose multiplied by lambda is Fn. We will see later on. We will, yeah, this is not, I will show you the one. Okay, so it's not transpose is fine. And then the second one is transpose. Correct? Is everything fine then?
This is inverse.
Sorry?
This is inverse.
S n, I think, right? Because A inverse, yeah, this one, A inverse is always a big problem for me. Yeah, so for this one, yeah, so this one is S inverse actually. So don't bother about this. You can look at the lecture note and on the textbook as well to see what is the correct inverse then. Anyway, so let's have this one. So now let's have to look at the dimensionality here. Oh, by the way, this one is also part of your assignment. So this one is part of your assignment. It's I'm going to say part 3. Part 3 is combination of full Bayesian and predictive distribution. Okay. So PU here, what is the dimension of PU? No. It's a future price. Future price is 1 by 1 because you only at that point what is the price? And this is MU 1 by 1 and everything is 1 by 1 is univariate version. So this 1 by 1. So this one has a problem. Then what is MN? MN is what is the dimension of MN? N by 1, right? So this one is N by 1. So that and phi here is it's not 1 by N actually. It should be M. It should be M. Let me think. So let's look at Mn. What is the dimension of Mn? So this is Mn, right? N by 1. Mn is N by 1. So this one is not N, but N by 1. So in this case, it has to be N 1 by N, right? Or in my notes, basically, I just change this to be transpose. So this one is transpose, means that it's 1 by N. And this one is N by 1, which is 5 bar X nu. Is that okay? Any objection here? Phi is the same as X, basically. X bar. Okay. Right. So X nu is again is 1 by 1. If it is 1 by 1, you can just make it 1 by 1, removing the I. I is like just 1, right? And then for the second term, it has to be 1 by 1. And Sn, what is the dimension of Sn? I think N by N. This one is already N by N. In that case, we have to have 1 by N, N by 1. N by 1 is actually N by 1 here is this one, right? This is 5. So we have to make it 5. This is 5 nu. And on the other side, it has to be becomes transpose of 5 nu. All right. Any questions here, anyone? So this is only for 1 point. Right? 1 point. You can expand it, of course. It is not going to be 1 by 1. If this PU is a variable, is a factor. So, and then you have how many data you want? What variable? Your Z, for example, Z is the number of the future that you want to predict. Then this one is Z by 1, this is Z by Z, right? And the rest is you can do it. It's not going to be 1 point in the future. But the probability that you have will be the probability of the joint probability of the future combined. If you have 2 in the future, then joint probability of the 2 points. Okay, so not individual points. Yes. What's the difference between the 2 version of the 5, the allocation of the 5? Like, the one you just now. Oh, right. So I didn't explain. So yeah, 5 here is actually matrix with the dimension of n by n, right? Phi. Again, if you have a difficulty with phi is equal to x. So phi is equal, if it is polynomial function, it is the same as x. And this is n by n. This is also n by n. Okay. So now if you look at the a here, your function a is a function there. This function a here, right? And a there, if you look at your corresponding function, is, sorry for the cluster. So this one a here is something to do with that one, right? With phi. Phi here, instead of a matrix, it is a vector, right? This one is a vector. This is 1 by n. Your vector here is n by 1. Means that your data is only 1. Your data is only 1, right? It means that your n here is only 1. So that's why your a here is equally phi nu, or phi nu because it's nu here, phi nu. Phi nu is a phi x nu. If you write it in the polynomial function, phi nu is identical to x nu bar. All right? So this is a vector. In our case, it's a vector. Good. Any other questions? Any other questions, anyone? Okay, so if there is no questions, actually that's all for our discussion on regression. So now we already know that if you want to know the probability in the future, you actually use this predictive distribution instead of full Bayesian on the training data. But the full Bayesian in the training data is still useful. It is used here, right? But now you can have full probability of your future price. Now the question is that is the storyline ends here? Well, no, actually no. There is a further problem with this. The problem with it is too much dependent on the training data here. You still use full Bayesian for the training data to solve the problem. The continuation of it, if you want to continue further, is called Gaussian processes. In Gaussian processes, you will no longer use this explicit solution from the full Bayesian. The expression is still the same. The expression is that we want to know the property of the price in the future. It's still the same, but the solution is different. And that one is called Gaussian processes. But we will not go that far. So we will stop here for regression. We will stop here for regression. And the next one will be what? After regression, we have another task. It's called classification. Okay. So the next one is classification. Okay, so before going to the classification problem, any questions for you so far, the storyline? Yes. Which one is transpose? So in equation 1 or equation 2? The blue one. Okay, so the blue one here. So let's name 1, 2, 3, 4, 5. Which one then? So okay, so not that one. Okay, so this one. So which one is transpose? The fifth last one. Oh, there is no transpose. It is inverse. It is inverse. Why is inverse? Well, I'm messed up. I often forget to put inverse in the equation. So it might be inverse here. So I forget to put this one inverse. Okay, so again, I often mess up, forget to put inverse in the explanation. But everything is correct on the lecture note or in the textbook. So look at the textbook or the lecture note for the correctness of the inverse. Okay. Any other questions? Any other questions, anyone? If not, I will briefly look at the discuss with you about classification. Classification, to be honest with you, it's more difficult than regression. It's more difficult than regression for mathematics. So please be prepared in the discussion of the classification. Okay, anyway, any questions before we move to classification? The introduction will not be too difficult, but I need to explain to you a bit on the classification, so then we can have more time to discuss the advanced topic. So let's move on to classification. Okay, so you know the classification problem, right? The classification problem is that if you have two classes, positive classes, and negative classes, for example, then our task is to, in this linear classification, we can just want to separate the two classes with a linear separator, linear line. So the green line here is our goal. It's not really our goal because it's the same as W, right? We know that W is the goal. In the end, we want to know, in the testing, we want to know whether if it is a point there, a query point or a testing point, what will be this query point belong to? Whether it belongs to the red or belongs to the blue. And further on, in the end, the goal and the end goal is that we want to know the probability of this. The same again as P nu P bar. So the goal is the same, that we want to have P nu with P bar. What is the probability of that green point belong to the blue line, the blue cluster, the blue class? Of course, in between, we also want to know P of W bar P bar. So this one is a full Gaussian, as we just discussed, and this one is actually a predictive distribution. So by the end of the first part of this module, we will get as much as possible the predictive distributions for the classification. Okay. So that's the goal. Okay, anyway, so let's take a look at as usual, we need to do modeling, data modeling. And essentially, we want to model the curve or modeling the line, the separating line. So in other words, we want to know about how we can have that, to model that line. So to model that line, what do you have in mind if you have to model that line? Modeling that line means that yn, right? Yxn. How do we model this one? How we can model the line? Using, it's not support vector. It's using polynomial function. The same again as what we did. But there's a good point there. I will explain to you later on
because in this case, because it's linear discriminator or linear function, we don't really need to have curve, right? In the previous one, we have curve. And because of the curve, we use polynomial function. So in this case, if we use polynomial function, what is the meaning of that? What is the meaning of that polynomial function? It's not curve. So if it's not curve, what kind of meaning of that polynomial function? So I will tell you that we will have sum of a t. So be careful here. We use t, no longer m, equals to 0 up to capital T. And we have wt xn t equals to, if we expand this, w0 plus sum of t equals to 1 up to t xn w xn t. Wt xn t. Wt xn t. So t there is in the parenthesis, means that it is not actually power. It's nothing to do with power, but I will explain later on what it means by that. So, and you know that this one can be simplified into W transpose xn bar. So now the question is that what is the meaning of this xn bar, right? So we ask ourselves what is xn bar. Understanding xn bar is very important in this classification. Let's assume that we have xn bar equals to, the first one is equal to 1. Equals to 1. And then we have xn 1, xn 2. Okay. So the meaning of this, in this case, is 3 by 1, xn is 3 by 1, is that we have two-dimensional space. We have two-dimensional space here. The x-axis will be xn1 or x1 basically. If it is independent of the index of the sample, it's x1. The y-axis so the y-axis is x2. Okay. Let me think. Okay, good. So if you have a sample, positive sample, negative sample, then you have the coordinate for x1, for example, take a value of 10, and the other axis, for example, the value is 2. It means that for your sample here, the coordinate will be 1, 10, and 2. Make sense? So if you have negative sample, and this one is 3, for example, and that one is 9, then the coordinate for this will be 1, 3, 9. That's the second sample. So if you name this one x1, if you name it this point x1, then x1 bar, this one x2 bar. Any questions here?
So D is equals to 3.
D in this case equal to 3, right? D equal to 3. Yeah. So now that's actually this one, right? Actually, we are talking about this xn. So now we know xn. Xn has multiple dimensions. In this case, xn occupy or live in two-dimensional space. Your data lives in two-dimensional space. Now,
what is the meaning of this yn? What is the meaning of that yn? Right? So if you look at this yn in the simple case, yn equals to W0 plus W1 x and 1 plus W2 x and 2. That's the meaning of yn in two-dimensional space. Remember that xn1 and xn2 is given to you. It's the data, right? Let me think. Yeah, so this one is a, sorry, I'm making a mistake. So let's make it easy. Let's just make it easy for you to imagine this one, because normally in high school you put it as x, and this one is put it as y, correct? X1 is actually x, x2 is actually y. So let's put that in that way. So W0 plus W1, x1, xn1 equals to x, right? Plus W2, xn2 is actually y. Now my question to you, what kind of equation is this? Assume that for simplicity, it is not necessary to be 0, but assume that it now is equal to 0. What equation is that? It is? Yeah, in this case, yeah, correct. Our plane is correct. But if we talk about two-dimensional space, it is just what? A line. So this yn is actually a line, your green line. And hopefully this green line will separate the positive and negative. It is a line if your data lives in two-dimensional space. Imagine if your data lives in three-dimensional space. Then it becomes a surface, a plane. If your data lives in more than three-dimensional space, your green line becomes a hyperplane. So yn is hyperplane. A plane, hopefully, that later on can separate the positive and negative. So again, the purpose here is the same as before, but the imagination is totally different. The complexity, the model complexity is nothing to do with your curve. The model complexity here has something to do with what? With the dimensionality of your space. The more dimensionality you have, the more complex your system will be. So this model selection, remember that you have a model selection problem, right? Model selection problem in regression in the curve fitting is that if your data is very complex, if your n is sufficiently high, then your curve can be very complex and positive. But in classification, it's nothing to do with your curve. In classification, if your data lives in two-dimensional space, when you look at data, it's only in two-dimensional space. So yeah, just for intuition, if your data is in two-dimensional space, but it's very complex, like this, it's two-dimensional space that's very complex. You cannot use a linear line to separate this. It's impossible to have a linear line to separate the positive from the negative. So what do? What you can do is to transform this into a higher space. Because if you transform this into a higher space, say that, for example, you transform this into three-dimensional space, the negative will be here. The positive, perhaps, the positive will be here. And in this case, you can have a hyperplane that separating the positive and negative. So why now in two-dimensional space it becomes complex? Because we see that as a projection of your space. You see it from the angle. If you see from that angle, then what you have is very complex distribution of positive and negative. But if you transform this into higher space, then they will separate. It's not necessary that in the three-dimensional space it will be separate immediately, but as long as you increase the dimensionality into 4, into 5, into 6, or even into 10,000 kind of dimensionality or 100 dimensionality, for example, you will always can separate the positive and negative. Because that is called overfitting. So overfitting in classification is very different from overfitting in regression. Overfitting in classification means that you can classify the two positive and negative 100% in the training. But in the testing, it's fair to separate the positive from the negative. Why? Because you choose too much dimensionality in your training process. And that is called overfitting for classification. It means that if you transform back into low dimensionality, if you transform back into low dimensionality, is that what you have is something that is very, very complex. In high dimensionality, it's not complex because in high dimensionality, that one becomes a hyperplane. But when you transform back into low dimensionality, it becomes very complex and can always 100% separate the positive from the negative. Does it make sense? Yes. It's not square, it's not power. Yeah, so there's a difference, good question there. It's a difference of regression. In regression, polynomial function is a power. But this one is nothing to do with power. It's just the index of your dimensional space. No, it's not a curved line. It's never be a curved line. By increasing the dimensionality, by increasing the complexity of the model, means that you want to find a hyperplane, still a hyperplane, but in much higher dimensionality than you can 100% separate positive from negative. Yeah, good question. Any other questions? Yes. So again, if you want to have, we do not know D, it's the same like we do not know N, right? But if you set your D so high, higher than what it should be, then it will always 100% separate the positive from the negative. In this example, well, this is a very simple example. In three-dimensional space, the actual data is lived into D. The actual data lives into D. Okay? But in 2D, we cannot separate positive and negative using linear line. So we need to transform this into a higher space. And the higher space here is a question mark. How much higher does it want to transform? Maybe 3, maybe 4, maybe 5. We do not know. But we know that if it's too high, 100, for example, it will overfit. Means that we can always 100% separate the positive and the negative. But if it is too low, for example, for this case here, that's the case there, if you transform it into 3D, it will not be overfit. It will not be overfitting. It might be underfitting. Underfitting means that you still cannot separate using plane for the majority of the sample. Does it make sense? So in this case, I can give you the exact illustration. So forget about this. So in higher space, in 3D space, for example, what you get is still positive or negative here, negative there, and also positive. but positive is also in the area of the negative. So in this case, even in 3D, you cannot separate the majority of the sign. So this is all under 50.
But the first example that you gave was only the line.
Yeah, probably. On the variables, yeah.
That's B equals B, right?
This one,
Yes.
t equal to 3. Yeah. T equal to 3 is equal to dimensional space because 1 is not equal to 3, just for the offset. So W0 is for the offset. Yeah, so this one is, you remember the function that you learned in high school that ay plus bx plus c equal to 0? C is actually W0. If it is hyperplane, ay plus bx plus cz plus b equal to 0. And if it is higher space, then you can extend yourself ay plus bx plus cz plus d whatever you call it, right? What is that? S, for example, plus d equal to 0, plus e equal to 0. You always have constant here. You always have constant, and this constant is W0.
Minus what? Not B. B over not something. B over not something.
So for this equation,
B minus what? Not B.
d minus 1. Yeah. Okay, so yeah, available. Yes, it's fine. D minus 1 is also. And that's something that you need to be careful because I don't really like to put d plus 1 sometimes. So you know what I mean by saying d, right? So this means that d minus 1 is 2. Anyway, so that's the method of small things. Any other questions? Any other questions, anyone, for this discussion here? All right, so if there's no questions, that's all today, and thank you, and I will see you again.
Thank you so much.